is Z control region. We don't have. They should be in principle. They should be always E equal to Z equal to E plus and E minus. But we still can get some opposite sign and same sign. The electrons even in the Z control region, and then because of the mismeasurement, the detector's mismeasurement, then using this one, then we apply the misidentified rate to this opposite sign real control region data, and then it will produce, some of them will be changing their ID, and will produce so-called after apply real Monte Carlo mis-ID compared with the same sign from measurement. And if they are totally not agreed, then something is wrong. But if they are more or less agreed, it means our mis-ID rate is almost is good, but the difference is our systematic error. So this is the second step. And then finally, we found it is good. Then apply this mis-ID rate to the real data to see finally how much the background is due to this charge mis-ID. And this is what we got. It's mis-ID is a function of the PT and the eta. And we got this one, and then we also have to validate what we found is correct. And this is what our result. In the Z control region, we got about those opposite sign Z's, which is dominate. Only 109 is same sign, which is as it should be, because it's we already selected is a Z control region. And then when we applied this the rate from the Monte Carlo, and then predicted the same sign should be about 120. So difference between 120 and 109 is our algorithm error, as a systematic error. So, but this is acceptable. So we set about 25% as a systematic error and uncertainty. But this is basically the algorithm half data-driven method is working. Now, the last, the most important background is fake electron background. And this is so important because at the beginning we did not really realize how can this jet misidentify as an electron. So actually it's very true because we consider its electron is purely from the electron identification for the isolation or this kind of things, but the jet also can be very possible pass all the requirements you are asking. So detail you can see the CMS they have the fake rate background. They have the very thick the analysis note. They analyze all of the data and have done about 20 people have done a couple of years on this study. The idea is further define the so-called analysis object, which is electron pass all the selection cuts. So it means if we can pass analyze the object AO, we consider this a real electron. Then if you're loading some criteria, for example, isolation cut from point 1 to point 6, then this object is no longer very pure electron. We call it a fakeable object. So we get the AO or FO. Then calculate the fake rate. It means possibility the FO still can passing AO selection from the jet dominated sample. Then we get the table of the weight, which is the fake rate as a function of eta or PT for this kind of selection criteria, the ratio of FO and AO. Then finally using this table, and we reweight them, the data, reweight them, And finally, we found how much is possibility of jet or non-prompt electron misidentified as a prompt electron. So this is the way they so-called fake rate. And choosing here is basically try to move the jet as a fake electron. Here, basically want to try to remove this prompt. Secondary, it has an electron not from vertex, but from secondary decay. So finally produce this kind of table. For example, here is the fake rate, and the PT between 10 to 15, and the eta between 0 to 1 is about 20% of possibility it is a fakeable object can pass analyzed project. So it means about 20% could be become real, is jet become electron. It's possible. And using this table to apply to the real data, and then has another weight strategy, and finally get how much is the real background from the fake rate. And then whether this fake rate algorithm is correct or not, and how to validation them, and using some Monte Carlo example with TD bar or WJet or the QCD and so on, and calculate the Monte Carlo truth and predict, and finally how much difference is about between 50% to about some is very good. So this is finally we establish this our analyze the error or systematic error or this algorithm error. So this is what we got. Then another thing is we want to, as I before, the fakeable object is defined loading something from point 1 to point 6 and so on. But this looks like a very artificial. And if point 1 not go to point 6, if we go to point 4, what happens? If we go to point 5, what happens? If your fake rate is very change very much, it means your algorithm itself is something is wrong and not stable. So we make the test. For example, if point 6, 4, 5, and then fake background how much, looks at it's almost remain about 20% because our error already considered about 30 to 50%. So okay, then even we did not have enough data, but we still try to reconstruct the mass. And this is our diagram you will see. And this Majorana decay go to W and the lepton. And this lepton we name them called dotmed lepton. And this one we call sister lepton. And this from experiment point of view, they are identical. You don't know whether this is daughter or sister. And if you look at the original theoretical paper, they said that this is very important combinatory background because you don't know how to reconstruct it using which lepton to which jet. Two jet, reconstruct W is clear, but which lepton reconstruct with this W to the Majorana neutrino, this is not very clear. They have, in the theoretical paper, they have a long discussion about this one. And this is our work. We found this in the Monte Carlo study. We found that the smaller of the PT of the lepton is more likely as a daughter. So this is something new in our study. So look at if we're choosing the second leading PT of the electron and we counter the W in the Monte Carlo, we found that 70% is correct for 50 GeV, and 52% for little bit higher mass is correct, but still bigger than 50. So particularly in the low mass region is quite good choice.
50% is already always true. So
always true, exactly. This is also sort of meaningless. It's like you get a coin always 50-50. So, but for the low mass region is almost like 70% correct. So if we make a choice, if we Majorana mass reconstruct, you need to pick the leading jet or second leading jet or random tag, and you will see whether they constructed with different mass and for the 50 or 120 and 170 is a lower second leading PT electron is a better choice. But anyway, improvement is not very much, and particularly if our data finally you will see our plot and not much data. If we have not 12 or less than 20 in one and we have a lot of data, we can see the conclusion much better. But here is just in our Monte Carlo study, we produce a lot, much better picture than this one. And then finally we get the result. And first of all, we divided the result into 4 different regions. One is the rose cut, which is only 20 GeV cut. Another signal region, which is we have applied missing ET cut, which is 50 GeV. And because our signal has no missing ET. And this is our result from standard model, background, and fake charge miss ID, and finally fake rate and total observed. And there's observed and the data has not significant exit. Then another is so-called control region, which is should have no signal because they have missing ET is greater than 50, and principle it should have not any signal. This is the result. And another, this mass plot, which try to recount this is data and this is the background. And if we put in different mixing element, and we can get this kind of stuff, and there's not exceed any mass peak or whatever, but of course there's not enough data also.
Oh, it looks slightly deficit.
Oh yeah, but this is depends on what kind of elemental parameter you put in. This is actually ultimately, yeah. It's either if we're using real mixing element, and this probably you can't see at all. Yeah. And then the tight uses 30, and this signal reading, which has a missing ET cut, and then also control reading should have no missing ET, and which gets this result. But this is the mass, and important conclusion is the background in the 2 control reading, which is missing ET greater than 50 GeV, and the background is almost consistent. It means in the background rich region, they are almost the same. So this means our estimation to the background is more or less correct. This is the reason why we want to divide our data in the so-called signal rich region and the control region, which are not significant. And this is all this part is almost standard from every CMS paper. Only last, like a background from charging miss ID is our number, and the background fake is our number. And any other numbers is looks like with all other CMS paper. And so finally, the important is want to beat the lab result. We want to get the same mixing element plot, and using standard power gauge to calculate the 90-15 confidence level, and then we get this plot. And as at the beginning, there's a plot from the L3 and the Delphi. They only come to here about the 90, and then we extended about to 205 GeV, and then we reach 1 is the loss of the sensitivity. So this is our result. As I said, the Atlas, after we published this paper, Atlas rising the jet ET cut to 40, and then they are plot up to 300 here. So, but they have a much wider this error bar. So, because they have stated much less, because after very tough cut,
The same data size or?
Same data size, yeah, same data, but then the error bar is larger than us, but the curve is extended to almost 300.
Well, you could have done it as well because you said with the tighter cut, the limit is better. So
yeah.
Optimize saying, given the data set, what is my optimal cut?
Yeah. And then for 2012 data is almost same. The total data is about less than 12, and the signal Monca generator is different because this is 8 TV, not 7, and then signal efficiency is almost same. And then the background and the estimate.
So for your 2012 data, why didn't you tighten the cut? You have a larger data set, somewhat higher energy. Why did you still use the 330 dB?
Because at that time we don't, we still think that actually after that only still very few events left. At that time we don't know what Atlas is doing. Actually, I really want to using 40 GB cut as well, riding because we already found an advantage from 20 to 30 as an advantage. Why not go more? There's several reasons because one is student RY is already graduated, he doesn't want to do, and the second one he also does not want to do because you have to repeat everything from scratch. Once you, because this 20, 30 or 40 GB cut is in the very first step. So yeah, so you have to repeat everything start from scratch. So anyway, and then this is exactly same like 2011 data, and one thing we did not do is combine 2011 and 2012 data, and there's software for the Higgs search, but there's no standard software to combine them because there's so we did not really combine, still separate with 2011 and 2012 data. But anyway, slightly almost the same, and get the 2012 data little bit lower. If we really want to see, here is about 20 GB behind compared with. If say 2011 data is 203, here is about 213, something like that. So anyway, we don't have any discovery. We just set the limit and beat the lab. This is all what we have. Okay, thank you.
But 2012 is in the same paper?
No,
only
our paper only
2011
2011.
So what is the publication plan for 2012 given your manpower crisis? Is it finished?
It's we decided that want to include email using 2012 data. Using email because email really we have to do. Email has a lot of advantage compared to E and email because you electron identifier, you can reduce a lot of background if you use email channel. But we stuck on the study the correlation between E and mu. And so this that's why we take a kind of, otherwise I thought it is should be trivial if we already identify electron, we already identify muon, but then we just very easy to do the yeah. But we should include in the email, I think.
How does the mu bound compare with EE?
Compare with EE, almost same result.
But mu phase rate background should be very different.
Not much different.
Not much different?
Yeah, not much different. Phase rate actually more or less same. And the muon has advantage, has no mischarge ID. This background is very small. Almost we ignore it. Yeah. Phase rate is almost same.
Really? So electron and muon phase rate is almost.
Yeah, almost the same.
Okay, so.
Thank you.
No questions? Oh, let's thank the speaker. Oh, okay. This is what of our CMS students.
Okay.
Sorry. I have a question related to the source or background.
Okay.
I remember from your slide you mentioned about the source or background is most dominated by the non-prime electron event, right?
Yeah.
And
No, this is secondary.
Secondary, oh, okay, not the first one. So then you have some correction or the measurement from data by Z control sample to correct the mischarge rate, and the other one is the faking rate from jet to electron.
Yeah.
So I'm curious about these two calculations for the WZ event, since your most background contribution from Monte Carlo are WZ. So how to explain these two correlation for WZ event?
So W decay electronically, for example, L to nu, and then top is go to W and B. B can decay to leptons. So this second electron decay from B can be confused as a new electron from the primary vertex. But with this fake rate method, have fake object which is required remove the vertex requirement, then those should be removed as a fake.
But we select the electron from Z first, and then we select jet from W. Is that true?
No.
No. Okay. So I misunderstood.
No. You talk about. Let me see. I think. Okay. Here. Right. Here is further you define very strict. So all this passing selection cuts very seriously. So supposing AO is all pure electron. There's no fake possible. There's no possible fake. Second way, losing something.